Hi, this is Dr. James Camp from Lee College in Baytown, Texas, and these are my comments on More About Classes, Chapter 14 of Starting Out with C++ by Tony Gaddis. As usual, with a few additions or changes that I've made along the way. Okay, the first thing we want to talk about is the idea of static members of a class. So to give some perspective on this, the idea of objects versus classes. Okay, a class is mostly used as a template for making objects. Each object is then an instance of a class, but each object has its own properties or attributes. That's what makes them different. You could have 3 different tree objects and they could each have a different height, a different age, all these properties or attributes that would make them unique objects. But what about the case where all objects of a class share a property in common? Okay, we talked last time about a class projectile that could model projectile motion. Well, assuming all of these projectiles are on the same planet, they all have the same acceleration due to gravity. So why make that a property of each individual object? Let's just make it a property of the whole class, which we might call projectile : G. Use the C++ scope operator to say that G is part of the class projectile. Or you might be tracking people's voting preferences, and all objects of the class voter or citizen or whatever you want to call them would share the same citizen : voting date. Okay. Again, no reason to have a different voting date for every single person when we all, Americans at least, all vote on the same day, the first Tuesday in November for whatever reason. And so we can again make voting date just a member of the class citizen instead of having to make it part of every single object. Some other examples. All objects of class American contribute to one population number. So if you want to have each person be able to reference the American population, there's no reason to have that as a separate variable for each person. Each person does not have their own population. So that keeps track of the entire population of American objects. Or all objects of class Camp family member, okay, if you're me or my wife or my sons, we all share the same address. Okay, we all have a different phone number because these days everybody has their own cell phone, but we all share the same address, at least until my kids start going off to college. So I might as well make address part of the Camp family member class instead of making it an attribute of each individual object. And finally, if I were to simulate the current COVID-19 virus, all objects of class human share the same death rate from COVID-19. It's the same roughly 1% death rate. No reason to vary the death rate by person, unless you want to start getting into, fine-grained demographics and say that the death rate is higher the older you are or something like that. But if we're just simulating a bunch of humans and we're not taking those fine-grained details into account, we could just define human : death rate and leave it at that. And then each human object could reference the same death rate. Okay, so what we've been talking about is that all the variables we created prior to today in the last presentation, for example, were instance variables. Okay, it's a member variable in a class. Each object has its own copy. Each object is an instance of the class, so each one has its own instance variables. That would be like each member of camp family would have its own height and weight and age and as I was saying, they each have their own cell phone number, but they each have their own favorite food, their own birthday, all of those things would be instance variables. But then there are some static variables that apply to all objects of the class. And we define that with the static keyword. So I would define, for camp family member, I would define address as a static string that just held the address of our house that we all live in. Static member functions are functions that are written to only access static member variables. So you may want your static variables to be private and have getter and setter member functions like we had before. Those would have to be, well, those would want to be static member functions. But you can also have a static member function that uses the voting date static variable to do some calculation, like how many days left until voting or something. So they don't have to just be getter and setter functions. They can do any number of interesting things, but they can only use the static variables because they don't belong to any instance of the class, and so they can't access instance variables. Okay, so here's a really simple example of a static member variable. We have a class tree that's modeling, I don't know, I suppose the trees that are planted in an arbor or something. And we want, the arborist wants to keep a count of how many trees we have. So doesn't make sense for each tree to have their own different number of trees. So we make that a static int object count. So you define it just like any other variable, but you prefix it with this word static that makes it belong to the class instead of to each individual object. Unless it's a constant, you have to define the initial value of it here outside the class. So we can put int tree : object count equals 0. And again, there's that C++ scope operator telling the compiler that object count belongs to the class tree. We don't, for some reason, use the dot notation for static members of a class. You can in other languages, C# and Java, for example, but in C++ we use the scope operator instead of the dot operator. Okay. And then we defined a member function called getObjectCount, and we just call it the way we call any other member function, pine.getObjectCount, but because the number of objects that it's referring to is a static number, it doesn't matter whether we call pine.getObjectCount or elm.getObjectCount or oak.getObjectCount, they'll all return 3 trees because that's the number of trees we have. Okay, all 3 of these instances, the oak instance, the elm instance, and the pine instance, all 3 point to this one static variable that belongs to the tree class. Okay. A static member function, same thing. It's declared with static before the return type. So you could have a static void, you could have a static int, a static, anything. So we say static int get object count. We add the keyword const here because we're not changing any data in this function. And then we return the global static object count variable. Now, remember, static member functions can only access static member data. So we couldn't take the height of one tree and divide it by the number of trees or something. And these can be called either by putting oak dot get object count, or you can use the scope operator and the class name and call tree : get object count. Okay. So this is the example. We've got a static int object count. We increment it every time we construct a new tree so that we have a total number of trees. Ideally, we should also have a destructor that minuses it. So if we ever get rid of a tree, we would count down. And then we have static int get object count that simply returns the value of object count. Okay. Static things are useful for also for kind of organizing your constants, your global constants, instead of just defining them as hanging out in free space up in the top of your program, like the acceleration due to gravity example that I gave at the very beginning. You can make your constants static members of classes, and then you can always, and that helps organize what sort of where to look up each of those constants, what they belong to. One example I like to use is that if I do a lot of unit conversions, I'll have a class convert, and all it will have are a bunch of static const double say inch to centimeter equals 2.54. Okay, and then later in my code I can write height of my chair or whatever equals if my chair is 2 feet off the ground, then or 30 inches off the ground or something like that, I can say height equals 30 times convert : inch to centimeter. Okay, and then it's very obvious what I'm doing. I don't have to stick a random so-called magic number into my code that is hard to interpret. Where did that number come from? I can, it's obvious that what I'm doing here is I am converting inches to centimeters. Okay. Next section, friends of classes. just as you might share the private details of your life with a friend of yours, a class can share its private members with a friend, which can be either another class or another function. So for example, you might have a friend function that prints out all the data in your class. It doesn't have to be part of your class. It can it can be a separate function, but it still has access to all the private members of your class because you made it a friend. For example, you might have a friend function set eval that takes int val and int. I don't understand that. But I don't have to understand that part. The important point here is that this is a friend function. You're declaring this function to be a friend of whatever class it's declared in. You can just declare it to be a friend of a particular class by saying friend void some class : name of the function, set num int num. So that's this function belongs to some class, but it's a friend of the class that's declaring it. You can even declare an entire other class to be a friend of this class. New class has friend class, and that means that all of the member functions of friend class can access the private variables of new class. This is kind of a dangerous thing to do. It sort of defeats the purpose of encapsulating your data as private, but if you have a overriding programming reason to do it, then it is built into the C++ language. Okay. As I was saying, one example that sort of comes to mind is you might have, class. Well, if we just stick with our class projectile that we defined a simulation for last time, it might have an int t for time in seconds, a double value x, and a double value y, and usual getters and setters and all of that, but these are all private. Okay. But then we can define, and there will be public get blah set blah. And of course a function called fly that makes the projectile fly. But then we can say friend void print location. Okay. And projectile. Okay. Projectile and projectile. And then later in our program we can write void print location blah, and within that we can just say cout x y. Okay, and we don't have to refer to them. We don't have to use the getter and setter functions. Well, we would have to say if this was projectile and proj. Okay, then we could say cout proj.x and just refer to it that way and not have to use the getter functions and setter functions and all of that. Okay, and so that's the real advantage of using the friend keyword. Okay. You can also use something called Memberwise Assignment to use the equal operator to just set all of the members of one function all of the members of box 2 will now be equal to all of the members of box 1. Okay, so if we look at this, before we do the assignment, we have a 10 by 10 box and a 20 by 20 box. Then in our program, we write box 2 equals box 1, and just as we expect from that statement, box 1 is still a 10 by 10, but box 2 is now a 10 by 10 box as well. Okay, but what if copying your object like that is a little more complicated? What if, for example, you have pointers to things? The default copy constructor copies field to field, and that works fine in many, perhaps even most cases. But what if your value is a pointer? Well, what we would copy is not the value, but the memory address that that pointer points to. So we'd end up with, if we just did A equals B, we'd end up with object A pointing to the same memory location, say holds number 32, as B is pointing to. And if you now say A dot set val 12 instead of 32, we're going to change the value of B dot value as well, right? Because we're they're both pointing to the same place. So what we need is a copy constructor that copies the value pointed to instead of the pointer itself. Okay. So a way to do that is to say, is to create a constructor that takes a some class object reference as a pointer, as a parameter, and then takes star object value, what it's pointing to, and copies it to star value. So now if we say A equals B, B is pointing to 12 in memory here. We create a new int. So A is now pointing to an empty int size box of memory. And then we copy the value over. So A is now pointing to a new memory space that has the same contents. Okay, so now if we say object 2 equals object 1, they'll both start out pointing to 5, but object 2 set val 13 means that object 2 can now be pointing to a different value than object 1. Okay, hope you understand that. If not, take a little bit of time to think about how you copy the value of something that is a pointer. Okay. Now, since the copy constructor holds a reference variable, it is possible to change the object. So to prevent that from happening, we usually declare it as a const object reference. Okay. So here's an example of a test score object that holds an array of test scores. And the copy constructor will take the student name and copy it, the number of scores and copy it, but then we'll create a new array of the right size, double of num test scores, and then we'll do a for loop to copy each score over one at a time. Okay. That's the proper way to do a copy constructor for something that has an array or a pointer or something like that as part of it. Okay. Copy constructors are one example of overloading or reusing operators that have other meanings in C++. Examples of operators that are commonly overloaded are, well, there is that equals operator we just looked at, but plus, minus, times, divided by, all of those operators can be overloaded so that you can use your objects to add them together. You can overload plus equals, minus equals, etc., so that you can add one object to another object. An example might be if you have a point, a class point that contains a int x and an int y, and so that marks a position in space, x, y, and you want to add 5 in this direction and 7 in this direction to get this new point right there. Well, you could create point, add point 5, 7, and then say my point plus equals add point, and it would take the 5 and the 7 and add them to that. Okay, much easier than trying to add, well, if you're doing a lot of these, it turns out to be easier than trying to add those one at a time, right? Okay. The way you overload an operator is you use the keyword operator followed by the operator symbol you're trying to overload. So operator plus or operator equal. If you're using operators, you're probably going to be using multiple objects of the same type, and so they're all going to have the same member names. Okay, they're going to have, if you're doing point void operator plus equals, and it takes another point, I think we do these as references too, and object maybe, okay, then you need some way to say that this x equals this x plus object dot x. Okay. Well, this is actually a predefined keyword built into C++, and it's defined as a pointer to your current object. So you would say this arrow operator x equals this arrow pointer x plus object dot x. Okay. Yeah. So here's how operator overloading works. Void operator equals constant, same class type. Sometimes it's called an R-val because it comes in on the right side of the operator. Okay, so if you have object 1 plus object 2, it's the one on the left side who gets the call. So this this would be equivalent to typing in code object 1 dot operator plus object 2. Okay, that's how C++ interprets that operation. Okay, so this just points out that you can actually do that. You can call object 1 dot operator equals object 2, but it's much easier and much more readable to just put the equal sign in there and say object 1 equals object 2. Okay, your overloaded operator can return a value. So we've been talking about operators that just modify a value so far, but what about operators like plus and minus? Typically, you would write those in a sentence that looks like A equals B plus C. Okay, so that would be equivalent to writing A equals B dot operator plus of C, which means operator plus has to return a value that can be passed to A through the equals operator. Okay, so operator plus or operator minus, as they use an example down here, has a double return value. So we could in this case say double A equals B minus C, where B and C are both points. Okay, and in this case what we wanted to do is say that we've got in our XY scheme, we've got point B and point C, and we want the straight line distance between them to be A, to be the distance, okay, to be the result of that this is B minus C, is that straight line distance right there, okay? So what we're going to do is treat that as a right triangle. And as you may know, C has a hypotenuse function that does the Pythagorean theorem for you. So we just return hypotenuse of, so in this case, we've got B and C here. So we're calling B dot operator minus C. So C becomes ampersand right, and A becomes this. So we could write this dot, this to arrow X minus right dot X, but the this is implied. So we can just use X minus right dot X, Y minus right dot Y. Okay. And then we use hypotenuse function to convert that into a double that represents the straight line distance between points B and C, and that works out. So you can have point A minus point B return a point, or you can have point A minus point B return actually a double or any other kind of value. Equals operator, believe it or not, has a return value because C allows you to chain equalses like this. Object 1 equals object 2 equals object 3. So the equals operator needs to actually return a value. And what you do is you just return this, return the ending value of your object at the end of its equaling. Okay. Note that on overloaded operators, you don't have to follow the strict meaning of the operator the way that everybody else always has. For example, when you do string plus string, what you do is you just stick one string at the end of the other string and you concatenate them, is the computer science term for that. You're not actually adding them member by member or something like that. You could define an operator where, a string minus a character just took that character out of the string. Okay. I don't think anybody has done that for C++, but you could. You could make your own string object that did that. But you cannot change the number of operands of the operator. You can't have, all operators, as far as I know, take one operand. You can't do multiples. And then certain operators can't be overloaded. The dot operator, the if-then operator, the scope operator, all those are permanently defined. Okay. You can overload the relational operators. So you could define operator equal or operator less than. Okay. Shouldn't put a space there. Operator less than. Those, however, have a return value of bool. Okay, you have to return a true or a false for those. You can also overload the bracket operator. This is one of my favorites. If you were creating a new list object that didn't work the same way as an array, but you still want people to be able to look up the third object in your list, you could overload the bracket operator and somebody could pass you 3 and you look up 3 would be the fourth the fourth object in your list. And then couple more little interesting things you can do with objects. You can overload the conversion operator. So there is an operator double that will cast your object to a double. So for example, if you had a feet inches object that kept the number of feet and the number of inches as a way to measure a height or a length or something, maybe you're keeping track of people's heights as a feet inches because that's how most people tell you how tall they are. Oh, I'm 6'3", or I'm 5'2", or 5'9", or whatever. But you want to be able to set a double equal to the number of feet with a decimal point for the inches instead of just inches. So you would calculate feet plus inches divided by 12 and return that whenever you're trying to set a double. So you could define feet, inches, height 6'3", that's my oldest son. He towers over me. And then you can define double h equals height. And so we'll do that conversion and pass 6.25 to h. Okay, last but not least, there is a technique called aggregation, which is where a class can be a member of another class. Okay, just as we had structs that could contain other structs, we can have classes that contain other classes. And it's the same notation as for structures within structures. So class student info may contain strings for first name and last name and address, city, state, zip. And then class student may contain a student info personal data, which contains all of those things. And so if we had student Stu, okay, we could say Stu dot, no, not Stu dot private, Stu dot personal data dot first name equals Fred. Except, of course, we couldn't do that unless we were a member, a friend function, because here we're accessing private data. So probably we would just call stu dot set name Fred, comma, Jones, and that would set those two values for me. This shows an example of a course which has to have an instructor and a textbook. Okay. So the instructor is actually another object which has last name and first name and office number and all sorts of stuff. And textbook is another object that has title and author and publisher and other sorts of things. Okay. So that concludes how to write an object part 2. There's actually one more piece, a part 3, on a concept called inheritance, where one object can inherit traits from another parent object that we'll talk about next week. Okay. Till then, keep learning, keep studying, and keep in touch.